Wisconsin, Milwaukee. The Science Bag, the television series where faculty members from university science departments share their special interests with you. And now, why does a spinning top stop? With Professor Robert Green, Department of Physics.
Good evening. Since I'm going to talk about tops tonight, spinning tops, let me show you a few items from my collection. A number of different kinds of tops. Most common ones familiar with you perhaps are twirlers, which you can twirl with your fingers or maybe with your palms. It's a Japanese top. Another classification of tops are supported tops. A top which is held in some sort of a frame while you rev it up to spin it. I have here a kind of a crude supported top from Indonesia, which is made of a section of bamboo and has a very simple way to hold it. Now, the tops of my generation, when I was a kid, tended to be spring-wound mechanical tops, which are sort of a combination of a twirler and a supported top, I suppose. It's supported by fitting a shaft fitting in a hole here, and it's spun by a spring. A top which is very ancient, or kind of top, is a whip top. In fact, references to these examples, these are found in Egyptian culture 2,000 years BC, and through many cultures since then. Basically, they're all the same. A top which is started spinning, and then its spinning is maintained by whipping it. I see a reference to medieval English tops where they're convinced that the best whip is one made of eel skin. Now, we don't have very many eel skins here to use. The top, which was an antique when I was a boy, which was the top of my parents' generation, is called a peg top. Now, you've seen them. They're sort of the stereotype top, conical. And as a kid, I didn't know how to spin these tops. Now, I guess what I did was extend my childhood enough years until I finally did learn how to spin them. But you wrap the string around the bottom of the top, and there's, of course, you can wrap the string two different directions. And there are many ways that you can throw it. And what I will hope to do is find one successful way. I'll try an overhand throw. I had the chance starting a couple of years ago to spend a year in Malaysia, where there are many traditional tops. Now, these are not kids' toys. These are spun by adult men. And these, obviously, are peg tops also. You can see several of them here. You might take a look at them later. These differ from most European or American peg tops in that the rope is wrapped around the top of them rather than the bottom. Now, one of the key to making this work is to wrap that rope tight enough that it doesn't slip. That is, that when you throw the top, it unwinds and hence gets the spin from the unwinding. And if it's not wound tight enough, it won't work. So I have my excuse established. If you look at these ropes, you'll see that the rope is tapered. It's a rope made by the top makers for this top. A subtle collection of features. Now, if you keep an eye on that, I think you'll see that it will spin for a while. But let's go to my version of the big top, which I might call, for obvious reasons, a tire top. What you see in the center of this is a shaft with a little ball bearing set in the end, just to make a smooth bearing surface. So we will move that over and set it on this pivot. Now you see it's not stable. It will fall over if it's not spinning. So we'll put it in a frame until we get it spinning. Now actually this tire is filled with water and weighs about 220 pounds. So we'll take a little doing to get it going, and hopefully it'll spin for a little while. So I have a fairly powerful drill here. Because I haven't spinning this fast. So there's my tire top. You notice that the Malaysian top is still spinning here. You might be interested to speculate on where tops were invented. Well, I think I know the answer. You find tops in almost every culture, and I suspect that as long as there have been children playing with their food. And that what is more natural after you've had all the food you want and you're tired of throwing the leftover nuts at your brother or sister to spin them. Or suppose you have a luscious strawberry, and presumably you've had a bunch of strawberries. Now that might be a little too soft to spin, but what if you stuck a twig through it to have a little bit of a base there, and then you tried to, whoops. Of course, the nice thing about some of these demonstrations is that when you're through, you can eat them. Or suppose, I mean, there's some things that were obviously made to spin. There's a lemon. Or if you get more ambitious after the strawberry works, and you have your apple. Now here's a twirler, but the kind where you can spin between your palms. Sometimes those work pretty well. Whoops. Or suppose you live where the fruit is hard and it grows on the trees. Or there's some things that when people started making tops, they copied. An acorn squash is obviously a homegrown top. And if you really got more ambitious, so I suspect that a top is one of those things that just wants to be invented, and that children playing with their food have invented again and again when their mothers weren't watching, right? The question which brought you here tonight was, why does a spinning top stop? Now this came up in a conversation with someone who's not particularly interested in these things just this last week. And the person, when she heard the question, sort of, I think her reaction indicated she thought it was a strange question. She said, well, it just kind of stops because it runs out of gas, doesn't it? And I got thinking about her answer, and it occurs to me that her answer is very much the kind of an answer that Aristotle would have given back in the very beginning of explaining things in a scientific manner. I mean, Aristotle wouldn't have asked the question because Aristotle was convinced that there were natural states for things, and the natural state for things on Earth was to be at rest. And so a top stops because everything stops. So the question Aristotle would have asked, why does that Malaysian top keep going for so long? Not why does it stop? And this is not perhaps too unreasonable. That is, he would observe that a horse pulled a cart and obviously exerted a force on the cart, and as soon as the horse stopped, quit pulling, the cart stopped. And so he would talk about something like an arrow flying through the air, and he would say, all right, as long as the bowstring is pushing the arrow, there's the force that keeps it going. But then once it left the bow, how did it keep going? That's what Aristotle had to explain. And they developed some ideas of air circulating around and kind of pushing the arrow from behind. And some of his followers then concluded that that would mean, or pointed out that that would mean that an arrow couldn't fly in a vacuum. And some people thought that was not a very reasonable conclusion, and they concluded from it that you could not have vacuum, that you could not have a vacuum because it would introduce this contradiction. Okay, but Galileo came along and started a different line of reasoning, and let me state it in terms that you're familiar with. Galileo would observe that if you took a block and you slid it across your living room carpet, it would go a short distance and stop. But if you took it to the vinyl kitchen floor and gave it the same shove, it would go quite a bit further. And if you went to some place where they had a polished, waxed wooden floor and gave it a shove, it would go quite a long distance. And in fact, if you went out on a cold morning after the ponds had frozen over in a cold night before, and gave that a shove across the smooth ice, it would go and go a long way before it stopped. And so Galileo got the idea that friction was a force. And he began to see that if you could reduce the friction, reduce the force on this thing, it would continue going forever. And so you see, this is quite a different attitude than Aristotle's. Galileo was suggesting that the natural state for something is to keep on doing what it's doing until some force changes it. Now, Newton was the person who formulated that idea very succinctly and came up with the formulation which explains so many things so well that it's called a law. It's called Newton's first law, and here it is stated sort of in the language of the 1600s that Newton would have used, saying every body continues in its state of rest or of uniform motion in a straight line unless it is compelled to change that state by forces impressed on it. Okay, different from Aristotle's idea. Totally opposite. The natural thing for something to do is whatever it's doing, and it will do that forever unless some force changes that motion. Newton came up with another well-defined relationship, which is the core of much of the work we do for moving things in physics. He came up with a mathematical relationship describing the interconnection of force, of mass, and of acceleration. Now, before we talk about Newton's relationship for these things, we need to be sure that we're all thinking about the same ideas. Force. I think your intuition is perfectly adequate there. Force is a shove, a push or a pull. Let's get mass for a moment. Acceleration. And I think you have a good idea of what acceleration is. Acceleration is a measure of how fast you're changing your speed if you're going down the road in a straight line. For instance, you could be going down the road at 40 miles an hour, down a straight road at 40 miles an hour. What's your acceleration? 0, if you're not changing your speed. If you want to change your speed, what do? You step on the gas pedal, sometimes called the accelerator, to change your speed to accelerate. Okay, so the acceleration is a measure of how fast you're changing your speed if you're traveling in a straight line. All right, you know that. Your intuition is right on that, I think. Mass, however, is a little tricky. Physicists make a big deal about the difference between mass and weight, and other people frequently don't. And on most days, that won't get you into any trouble. But occasionally it will. The reason it won't get you into trouble is you say, okay, there's a brick, and it has some mass. And if I take 2 bricks, it also has some weight. You know how much a brick weighs. If I take 2 bricks, I have twice the mass, but I have twice the weight. So what's the deal? Physicists will distinguish 2 different characteristics of mass. One is weight, which you're all familiar with, and the other property of mass is inertia. Now, let me point out where you can get in trouble with this. But we really talk about the weight of that thing. The weight of that mass is the force with which, the gravitational force with which the Earth pulls on it. That's the weight. Now, suppose on your next trip to the moon, you take this brick with you. You've heard the rumor that things weigh less on the moon, haven't you? Like 1/6 of what they weigh on Earth. Well, you see, already we've warped our definition of weight, because now on the moon you're not talking about the attraction of the Earth, but the attraction of the moon. And it's less. This weighs less, but something is the same. It's the same quantity of material. The thing that's the same is the mass. And the property of inertia which I think you have a feeling for, and what we're going to talk about here, is the same no matter where you take it, on the Earth, far away from the Earth, on another planet, wherever. So, the property of the mass that we're considering here is the inertia. And Newton's connection between these things is very simple. It's that force is exactly equal to a mass times an acceleration. If you exert a force on a mass, it produces an acceleration. This is an equation. You can put numbers in it. If you know two of those things, you can calculate the third one. If I tell you what force I'm going to put on how big a mass, you can calculate the acceleration that will result. All of a sudden, look, this mass has been accelerated, so much mass has been accelerated so much, you can deduce how much force there must have been pushing it. Right. It's a specific mathematical relationship which is the basis for so many useful things that, again, it's called a law. It's called Newton's second law.
¿Cómo se ve eso?
Now let me point some things out. Suppose what I'm going to do here is to show you that I'm going to put a bigger force on the same mass as before and ask you what happens to the acceleration. Well, if the left side of the equation is bigger and the mass is the same, the acceleration must be bigger. Right. If this smaller number times a bigger number here is going to be a bigger number here. All right. Now, you knew that without doing this. If you push harder on something, it's going to accelerate faster. Sure, you know that. You know that. Let me try another one. Suppose I put the same force on a smaller mass. What kind of acceleration are you going to get? A bigger acceleration. And you sort of know that too, don't you? If you push on a small mass, you're going to get more acceleration. Well, let's show you that. We have over here some rocket ships, which are really two painted pieces of wood. Now and in the back of the rocket ship, we have a hole, and in it we have stuck a little CO2 cartridge. So, if we puncture the back of that cartridge with a nail, the CO2 should rush out, provide a thrust, which should propel these rockets off this direction. And so, both of these rockets are going to get the same force because we have the same cartridges in both. But the red one is described by the top equation there. That is, this is the mass described in the top equation. You see, this mass is smaller, described by the second equation. And so we give the same force on two different masses. Which one would you expect would accelerate faster? Green one. So would I. But let's check it out. Okay. All right, this is just a little block to hold the nail. Very sophisticated launching system here. I think we should have a countdown, however. 5, 4, 3, 2, 1. Whoa! What if I used a very large mass? If I use a very large mass, the answer is that for some reason I'm going to get a very small acceleration, right? Right. Okay. The mass I'm going to use is a locomotive. a magnificent locomotive. It's so big that I couldn't get it in the lecture room. So I'm going to have to ask you to imagine it. Look at my magnificent locomotive. It's 1860 vintage, has a big wood-burning smokestack on it. Can you see that? Right behind it, there's the brass bell with the chain that goes back to the cabin so the engineer can ring the bell. See the two big driving wheels up front here, the red cowcatcher, and the brass headlamp just in front of the smokestack. It's a magnificent, very massive locomotive. In fact, this locomotive is better than any real locomotive because it has perfectly frictionless bearings. No friction at all, but tremendous mass. So, I need someone to help me move my marvelous locomotive. Let's see, this is a special job. Who can do this the best, I think? I'm not sure. I think this is what happens when you don't charge admission to these things. Oh, all right. Come on down. We'll give you a chance. I mean, there are lots of others who would be glad to help, right? Okay. Look, can you see? Can you see my look? If you're going to be able to help, can you see my locomotive? Oh yeah. Well, yes. All right. Very good. Okay. What I want you to do is help me. Now this is serious now. I mean, sometimes you guys do a lot of clowning around, but you're okay. All right. Look, I need. Okay, I want you to help me move this locomotive. Are you up to that? I'm not sure. I'm not sure, but we made a mistake here. No. Train engine, locomotive. No. Thank you very much. I think maybe we should get some. Oh. No. This isn't going to work. Do we have another volunteer? I think. No. Let's see. Who? We need another. Maybe. What do you think? All right, let's give him a try. Now. All right. Now look. What? All right, you see my marvelous locomotive of great mass, but frictionless bearings. So, it's very great mass, so you can push very hard on it. So I want you to push on it and see how it responds, this object of great mass, to your force. All right, now concentrate. Yeah. Yes. Very good. Thank you very much. Wait. Don't let it hit that wall. If you let it hit that wall, we'll collapse the lecture room. I didn't get your name. Never mind. The card says Ron Anderson, instructor of stage movement, theater department, UWM. Thank you, Ron Anderson. Okay. There are two lessons to be learned from that demonstration. The first idea is, to accelerate a mass, you have to apply a force. If it's a big mass, you have to apply a big force to get an acceleration. If it's a very big mass, you apply a force, you're going to get a small acceleration with a modest force. The second thing is that once you get something moving, to stop it, you also have to apply a force. Now, if we do this mathematically, we'll describe the slowing down also as an acceleration. We'll have a negative value if the speed is diminishing. And to do the mathematics, then we've got to consider forces in one direction to be positive quantities and forces in the other direction to be negative quantities. But what I want you to understand is that to slow something down, to give it a negative acceleration, you have to apply a force in the contrary direction. Clear, right?
If you'd like to talk over what you've seen and heard so far on the Science Bag, now's a good time to take a break. When you're ready, press the play button to continue.
Now we're ready to talk about rotary motion. Rotation motion. We can derive from Newton's second law another expression that is analogous to this for rotation. I'm not going to derive it in the mathematical sense. I'm going to show it to you and try to make it intuitively clear of what it means, that it is the equivalent of this expression for rotation. Okay. When you're trying to get something to turn, what serves a function of force for that? Well, you have some information about that. If you have a bolt that is rusted, or that you want to turn, you put a wrench on it, and you pull it. And if you can't somehow budget with that, what do? You get a bigger wrench. Or more specifically, you get a wrench